The universe is a vast, seemingly unending marvel of existence. Over the past century, we've learned that the universe stretches out beyond the billions of stars in our Milky Way, out across tens of billions of light years, containing somewhere around 2 trillion galaxies all told. And yet, that's just the observable universe. There are good reasons to believe that the universe continues on and on beyond the limits of what we can see. The question is, how far does it go on? Forever? Or does it close back upon itself at some point? All this and more will be discussed in today's episode. To find out the answer to this specific question and so much more, let's take a look at what our universe is like today. The universe is cold and clumpy today, but it's also expanding and gravitating. When we look to greater and greater distances, we see things as they were not only far away, but also back in time, owing to the finite speed of light. The more distant universe is less clumpy and more uniform, having had less time to form larger, more complicated structures that require more time for gravity's effects to take place. The early, distant universe was also hotter. The expanding universe causes all the light that travels through the universe to stretch in wavelength. As the wavelength stretches, it loses energy, becoming cooler. This means the universe was hotter in the distant past, a fact we've confirmed through observations of distant features in the universe. We can measure the temperature of the universe as it is today, 13.8 billion years after the Big Bang, by looking at the leftover radiation from that hot, dense, early state. Today, this shows up in the microwave portion of the spectrum and is known as the cosmic microwave background. Coming in with a black-body spectrum and a temperature of 2.725 Kelvin, it's easy to confirm that these observations match with an incredible precision the predictions that arise from the Big Bang model of our universe. Moreover, we know how this radiation evolves in energy as the universe expands. A photon's energy is directly proportional to the inverse of its wavelength. When the universe was half its size, the photons from the Big Bang had double the energy, while when the universe was 10% of its current size, those photons had 10 times the energy. If we're willing to go back to when the universe was just 0.092% its present size, we'll find a universe that's 1089 times hotter than it is today, around 3000 Kelvin. At these temperatures, the universe is hot enough to ionize all the atoms in it. Instead of solid, liquid, or gas, all the matter in the entire universe was in the form of an ionized plasma. The way we arrive at the size of the universe today is through understanding 3 things in tandem. First, how quickly the universe is expanding today, something we can measure via a number of methods. Second, how hot the universe is today, which we know from looking at the radiation of the cosmic microwave background. And last, what the universe is made out of, including matter, radiation, neutrinos, antimatter, dark matter, dark energy, and more. By taking the universe we have today, we can extrapolate back to the earliest stages of the hot Big Bang and arrive at a figure for both the age and the size of the universe together. From the full suite of observations available, including the cosmic microwave background, but also including supernova data, large-scale structure surveys, and baryon acoustic oscillations, among others, we get our universe. 13.8 billion years after the Big Bang, the edge of the observable universe now would lie about 46 billion light-years away in every direction. That means the observable universe is thus a sphere with a diameter of about 92 billion light-years and a volume of about 410 nonillion or 410,000 billion cubic light-years. That scale is just unimaginable. Anyone would feel overwhelmed to go straight to such magnificently large scales that span tens of billions of light-years. So, to help you better understand the scale of the universe, we just have to build up a little bit at a time. Let's start at the beginning with something more familiar and smaller that we know how to measure the size of: the Earth. As humans move farther and farther from Earth, you get to see what it's truly all about. It's a spinning, nearly spherical ball, about 13,000 kilometers in diameter. From only tens of kilometers up, you can start to see its curvature, and once you're a few thousand kilometers away, you can take the full planet in one hemisphere at a time. Earth is extremely large compared to the scale of a human, but humans have ventured far enough away from planet Earth to obtain precisely this view. On the solar system scale, our planet is just a pale blue dot, as described by scientist Carl Sagan. This image of Earth is one of 60 frames taken by the Voyager 1 spacecraft on February 14, 1990, from a distance of more than 6 billion kilometers. In the image, the Earth is a mere point of light, a crescent only 0.12 pixels in size. It is the most impactful picture ever taken in the history of mankind. In the incredible words of Carl Sagan, "Look again at that dot. That's here. That's home. That's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives." However, the Earth is on the small side compared to many of the other bodies in our solar system. Uranus and Neptune are each about 4 times the diameter of Earth, while Jupiter and Saturn are more like 10 to 11 times our planet's diameter. The Sun, the largest object in our solar system, is a staggering 1.4 million kilometers in diameter, some 109 times the diameter of Earth, and capable of fitting more than 1 million Earths inside of it. But the individual objects are easy to comprehend if you're already the size of the Earth. And from the perspective of the Earth, it makes sense not only to look at the objects themselves, but the scales at which these objects move around one another, on the scales of planetary orbits. The Earth is the one we're most familiar with a mean distance from the Sun of 150 million kilometers. But this distance, the Earth-Sun distance, is only a little more than 100 times the size of the Sun itself, which is only a little more than 100 times the size of the Earth itself. All of a sudden, by just going up a little bit, from on Earth to above Earth's atmosphere, and by looking at the other objects in our solar system, we've gone from the scale of a 1.5 to 2 meter human to a 150 billion meter orbit around our Sun. Of course, our Sun is just one of a great many stars in the Milky Way. So the next step up is from the scale of things in our solar system to the nearest stars. This is a huge jump, but one that we can comprehend if we now begin our starting point where our last endpoint left off, at the scale of Earth's orbit. Other planets, of course, are farther away from the Sun than Earth is. Jupiter's orbit is about 5 times the diameter of Earth's. Saturn's is 10 times as large. Uranus's is 20 times as great. Neptune's is 30 times as great. The Kuiper Belt extends out to about double the extent of Neptune's orbit, and while there are a smattering of other objects beyond that, you have to go out to around 1,000 times Earth's orbit before you reach the innermost portions of the Oort cloud. But the Oort cloud goes out for tens of thousands of times the Earth-Sun distance, perhaps out to even more than a full light year. And then, once you start reaching distances of a few light years, you finally reach it. The next nearest star to Earth, Proxima Centauri, located 4.2 light years away. Stars are separated by distances that are usually measured in light years, and they add up fast. There are hundreds of stars within 25 light years of us, and that number rises up to more than 10,000 stars if you draw a sphere just 100 light years around Earth. At this scale, you start to notice that there are directions in space where there are more stars, and other directions have fewer. You're starting to see the structure of the Milky Way. In the direction of the galactic center, as well as throughout the plane of the Milky Way, and particularly along its spiral arms, stars are denser and more numerous. Away from them, less so. All told, a galaxy is a collection of an enormous number of stars, but not an incomprehensibly large one. The Milky Way is a little over 100,000 light-years in diameter, which is to say that if a 1.5 to 2 meter human being lives on a 13,000-kilometer wide Earth, then that's the same ratio as the distance to the inner Oort cloud to the size of the Milky Way. Humans to Earth is the same as the size of Earth to the distance to the inner Oort cloud is the same as the distance to the inner Oort cloud is to the size of the Milky Way. And things, believe it or not, get easier from there. Stars are tiny compared to the distances between them. If the sun were a grapefruit in Seattle, WA, then the next nearest star would be a grapefruit in New York. But galaxies are not tiny compared to the distances between them. If the Milky Way were a grapefruit in Seattle, Washington, then Andromeda, the local group's largest galaxy located 2.5 million light-years away, would be a grapefruit in the same room, only about 3 meters away. In fact, the Virgo supercluster, spanning perhaps 100 million light-years, contains thousands upon thousands of large galaxies, and that would be like having thousands of grapefruits clustered and clumped together in groups over the span of about a single city block. In fact, the large-scale structure of the universe is kind of like that. There are hundreds of billions of grapefruits and tens of trillions of, say, oranges, mandarins, and kumquats that are smaller versions of galaxies, distributed across just under 500 such city blocks in all directions in all 3 dimensions, with ours, containing the Virgo cluster located at the center. If 100 million light-years is well within our local supercluster, then it's only some 460 times that distance to the edge of the observable universe. From the scale of a human to the scale of the observable universe seems incredibly daunting. Humans are a couple of meters in scale. The universe that we can see extends for some 46 billion light-years in all directions. That means the observable universe, in terms of diameter, is nearly a full 27 orders of magnitude, or a factor of 1 octillion larger than a human being. And that's the limit of what's observable. Any farther than that, and even something moving at the speed of light since the moment of the hot Big Bang, will not have had sufficient time to reach us. As time goes on, the age and the size of the universe will increase, but there will always be a limit to what we can observe. So what can we say about the part of the universe that's beyond the limits of our observations? We can only make inferences based on the laws of physics as we know them, and the things we can measure within our observable universe. For example, we observe that the universe is spatially flat on the largest scales. It's neither positively nor negatively curved, to a precision of 0.25%. If we assume that our current laws of physics are correct, we can set limits on how large, at least, the universe must be before it curves back on itself. Observations from the Sloan Digital Sky Survey and the Planck satellite are where we get the best data. They tell us that if the universe does curve back in on itself and close, the part we can see is so indistinguishable from uncurved that it must be at least 250 times the radius of the observable part. This means the unobservable universe, assuming there's no topological weirdness, must be at least 23 trillion light-years in diameter and contain a volume of space that's over 15 million times as large as the volume we can observe. If we're willing to speculate, however, we can argue quite compellingly that the unobservable universe should be significantly even bigger than that. The hot Big Bang might mark the beginning of the observable universe as we know it, but it doesn't mark the birth of space and time itself. Before the Big Bang, the universe underwent a period of cosmic inflation. Instead of being filled with matter and radiation, and instead of being hot, the universe was filled with energy inherent to space itself, expanding at a constant exponential rate and creating new space so quickly that the smallest physical length scale, the Planck length, would be stretched to the size of the presently observable universe every 10 to the power of negative 32 seconds. It's true that in our region of the universe, inflation came to an end. But there are three questions we don't know the answer to that have a tremendous influence on how big the universe truly is, and whether it's infinite or not. First, how big was the region of the universe, post-inflation, that created our hot Big Bang? Next is the idea of eternal inflation, where the universe inflates eternally into the future in at least some regions, correct? And finally, how long did inflation go on prior to its end and the resultant hot Big Bang? It's possible that the universe where inflation occurred barely attained a size larger than what we can observe. It's possible that any year now, the evidence for an edge to where inflation happened will materialize. But it's also possible that the universe is googles of times larger than what we can observe. Until we can answer these questions, we may never know. Beyond what we can see, we strongly suspect that there's plenty more universe out there just like ours, with the same laws of physics, the same types of physical, cosmic structures, and the same chances at complex life. There should also be a finite size and scale to the bubble in which inflation ended, and an exponentially huge number of such bubbles contained within the larger, inflating space-time. But as inconceivably large as that entire universe, or multiverse if you prefer, may be, it might not be infinite. In fact, unless inflation went on for a truly infinite amount of time, or the universe was born infinitely large, the universe ought to be finite in extent. However, the biggest problem of all is that we don't have enough information to definitively answer the question. We only know how to access the information available inside our observable universe, those 46 billion light-years in all directions. The answer to the biggest of all questions, of whether the universe is finite or infinite, might be encoded in the universe itself, but we can't access enough of it to know. Until we either figure it out or come up with a clever scheme to expand what we know physics is capable of, all we'll have are the possibilities. In addition, note that, extremely recently, dark energy has come to dominate. As we move forward into the future, it will be the sole determining factor in the universe's expansion rate. As the universe continues to expand, the matter density, both normal and dark, continues to drop, but the density of dark energy will remain constant. Because the expansion rate is proportional to the energy density of the universe, that means the constant density that dark energy gives you means the expansion rate asymptotes to a constant. Based on the current expansion rate as observed by Planck, 67 kilometers per second per megaparsec, that means two big things for the future. The expansion rate will asymptote to 55 kilometers per second per megaparsec, when only dark energy is important, and this expansion rate will cause distant objects to recede in an accelerating fashion, and the universe will expand exponentially. Think about why this is. Why a constant expansion rate means that distant objects accelerate and that the universe expands exponentially. Imagine a galaxy 10 mpc away. If the expansion rate is 55 kilometers per second per megaparsec, then it appears to move away from us at 550 kilometers per second due to the universe's expansion. Over time, it moves farther and farther away. How fast does it appear to recede then? When it's 10 megaparsecs away, it recedes at 550 kilometers per second. When it's 20 megaparsecs away, it recedes at 1100 kilometers per second. When it's 40 megaparsecs away, it recedes at 2200 kilometers per second. When it's 80 megaparsecs away, it recedes at 4400 kilometers per second. And so on. The more time goes by and the farther away the galaxy is, the faster it recedes from view. But here's what you have to realize. The amount of time to go from 10 to 20 mpc is the same as to go from 20 to 40, or 40 to 80, or 1000 to 2000, and so on. In a universe dominated by dark energy, this is how exponential expansion works. So if we wanted to plot out what the universe's apparent size in radius is as a function of time, all we'd have to do is run the math. The results are simple, straightforward, and easy to read off. If you hold a ruler up to the graph, you can see that in the very distant past, the line has a certain slope that indicates radiation domination. In the more recent past, the universe was matter-dominated, where the slope of the line changes. And then the line changes into an exponential curve. When dark energy takes over from matter, as the matter density drops further. That's where we've just started living today. Our observable universe, as we know it right now, is 92 billion light-years in diameter. At 13.8 billion years of age, that's how far we've managed to come. When will the universe reach 100 billion light-years in diameter? When it's 14.9 billion years old, just 1.1 billion years from now. At that point, the universe will be 73% dark energy, and the expansion rate will have dropped to 65 kilometers per second, per megaparsec. Not much of a change. But as we go forward in large steps, the changes get very dramatic. By time the universe is 24.5 billion years old, a little more than 10 billion years in the future, it will be 94% dark energy. The expansion rate will be 57 kilometers per second per megaparsec, but the observable universe will be 200 billion light-years in diameter. At an age of 37.6 billion years, the universe will be 99.4% dark energy. The expansion rate will be 55.4 kilometers per second per megaparsec, and now the universe will be 400 billion light-years in diameter. And now, every 12.2 billion years after that, the size of the universe will double, with the expansion rate leveling off at 55.4 kilometers per second per megaparsec. This means the universe will hit 1 trillion light-years in diameter when it's 54 billion years old, 10 trillion light-years at 86 billion years, 100 trillion light-years at 118 billion years, and a quadrillion light-years in diameter at 149 billion years. By time the universe is 10 times its current age, it will be nearly 10,000 times its current size. That's the power of exponential expansion. As it stands today, the observable universe contains somewhere around 2 trillion galaxies. As we move ahead into the very distant future, all of that matter that isn't a part of our local group will recede from us towards these distant horizons of the universe. What's now contained within a sphere that's 93 billion light-years in diameter will be stretched out over larger and larger volumes, leading to a universe where the average density eventually drops to zero, and does so uncomfortably quickly. If you were born when the universe was 10 times its current age, Milkdromeda, which is what our local group will merge into, would be the only galaxy you could see in the universe for trillions of light years. Enjoy our universe the way it is while we're here, because it's expanding away from us at this exponential rate with every moment that passes. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.